All right, so really quickly, a couple people had questions about their piecewise functions and how to kind of see the difference between them. So I know that it's not in perfect notation over here, but for each one of these, you guys can imagine that you have, a little brackets and then f of x equals, I know it's kind of small, but we'll say that, f of x equals that, and then we have over here our domains for each one of these. All right, so you can see negative 2x plus 6 when x is less than 2, that's this line coming in right here. And then x squared minus 1, that's this line coming in right here when x is greater than or equal to 2. So open circle here because it's not equal to, closed circle here because it is equal to. The limit, so if I write here the limit as x approaches 2 does not exist. This function does not exist because the left and right hand limits do not equal each other. So obviously that's pretty apparent from the graph, but if you didn't have the graph, you could just look over here and plug in 2 to each one of these. So if I plug in 2 to the first one, I get negative 2 times 2, that's negative 4, plus 6, that would be 2. And you guys can see visually that it's coming down here to 2. And then if I do the other one and I plug in 2 from the other side, I would get 2 squared, which is 4, minus 1, that would be 3. And again, you can see visually that it's coming down from this side to 3. And because those are not equal, 2 is not equal to 3, then the limit, therefore, does not exist. Let's look at another example. In this one, okay, it's the exact same graphs again. The limit from this side equals 2, the limit from this side equals 3. The only thing is that now we have 2 open circles, okay? So now it's not equal to on either one of these, and you can see that that equal to disappeared right here. Again, the limit still doesn't exist. The limit from the left is 2, the limit from the right is 3. Therefore, because they do not equal each other, the limit does not exist. Doesn't matter if the dot is filled in or not. So remember on this first one, the dot was filled in. On this one, the dot is not filled in. Honestly, it doesn't matter. The limit only cares about what the function is going to, not what the function actually equals. This one, again, the same functions, but look that I've added in an extra point right here. So I've added in the point 2, 1 so that it shows up down here. Same thing as the last one. The limit does not exist because from the left it's going to 2, from the right it's going to 3, and the function equals 1. So we got 3 different things happening here. But essentially the limit still does not exist because there's still this gap right here. Okay, so whenever there's a gap between the two, the limit will not exist. And you can again check that. You don't have to graph it. You can just check it by plugging 2 into the function, and you'll realize that the 2 are not equal to each other. All right, so let's talk about one where the limit does exist. Okay, looking here. I know that it doesn't exist over here. You guys can see that rational function. Don't even worry about that right now. We're just worrying about this point over here. So the limit as x approaches negative 1, the limit as x approaches negative 1 of this function, notice that from the left, it equals negative 1/2. From the right, it also equals negative 1/2. So because the left and right hand limits are equal, therefore the function has a limit, and that limit would be negative 1/2. Now you might be saying, Ms. Martinez, there's a hole in the graph. Again, that's okay. The function itself does not need to exist in order for the limit to exist. The limit cares about what's happening around the point, whereas the function itself is what's coming defined at that point. So we don't care that it's not defined. The limit will still exist. Example number 4 or 5, whatever we're on. 5. Okay, this one. Look here. The limit is still going to negative 1/2. So if I say the limit as x approaches negative 1 of this function still equals negative 1/2. Okay, the left and right hand sides are still going to negative 1/2. All right, but the function is defined up here. That's okay. Again, we don't care what the function is defined. We don't care if it is or not, or if it's defined somewhere else. We only care about what the limit is going towards. So the left and right hand sides, we care about what that's going towards. With that said, if you didn't have the graph again, you could just look over here, okay, and then plug in negative 1/2. Obviously, if you plug in negative 1/2 right here, I'm sorry, not negative 1/2. If you plug in negative 1, you're getting an undefined for that. But remember that little trick about how we can factor out the numerator and factor out the denominator? So if I do x plus 1 divided by x plus 1, x minus 1, you'll notice that the x plus 1's cancel. So I'm left with 1 over x minus 1. And then when I plug in that limit that I'm looking at, when I plug in negative 1 into here, I get 1 over negative 1 minus 1, which is negative 1 over 2. So that's where I get the negative 1/2 from. So again, you don't necessarily need the graph what you need to know is that you can use algebra as well to solve these ones. So sometimes you might have something like this where you need to use your little rules about how to factor them in order to solve that. So again, with this piecewise function, you just had to factor it and cancel, and then you could figure out what the limit was. And just to reiterate one more time, the limit goes to negative 1/2 even though the function equals 1. We don't care what the function equals, we care what the limit's going towards. And last but not least, this last example, you'll notice that my piecewise functions are the same, so technically there's still a hole in the graph right there. But notice that all of a sudden I added this point at negative 1, negative 1/2, and it filled the hole, okay? The limit is negative 1/2. It just so happens that the function also equals negative 1/2, okay? The limit of this function up here goes to negative 1/2 at negative 1. The function also equals negative 1/2 at negative 1. We can kind of visualize that like this function is filling the hole. So there was a hole there, and it got filled by this point, okay? So it just so happened that that point got placed perfectly on this line so that it filled the hole perfectly, okay? We call that continuity. We'll learn about that later, but we call that continuity, where now all of a sudden you had a hole, and now you don't have a hole anymore because you filled it with this extra point, okay? Continuity is not important for tomorrow's test, but the property of the fact that the function doesn't necessarily need to equal the limit, but that you can make them equal the limit. Okay, that's an important part. So I hope that helps. Please School Loop message me if you guys have any questions, and we'll see you guys on Friday. But tomorrow, don't forget you have that big test, so please make sure to study.